This is our Sun, a relatively quiet star of average size, larger than a red dwarf but not a giant. Nevertheless, compared to our world, our Sun is unimaginably large. It has a diameter 109 times larger than Earth and makes up about 99.86% of the mass in our solar system. Then, there are the galactic supergiants. A well-known example being Betelgeuse. It is one of the largest known stars and has a diameter of approximately 1.4 billion kilometers. For comparison, our Sun has a diameter of 1.4 million kilometers, meaning Betelgeuse is about 1,000 times larger than our Sun. These are sizes that are difficult for us to comprehend and visualize. But, is this the limit of a star's size? Is this the maximum size a star can reach? To understand this, we first need to know how it is even possible for stars like Betelgeuse to grow so large, and why they do so. It all begins with a single force: gravity. In space, there are enormous clouds of gas and dust. Imagine one of them slowly collapsing because the pieces attract each other. The more material comes together, the greater the pressure becomes inside, and the hotter it gets. Eventually, it gets so hot that a kind of gigantic, never-ending fire ignites in the core of the forming star. The star begins to shine and burn. What was once an invisible cloud of gas and dust is now a radiant and hot star. Now something interesting happens. This fire inside pushes outward, and gravity pulls inward. And as long as these two forces are in balance, the star remains stable. Neither wins, neither loses. The star is suspended in a perfect equilibrium, so to speak. This is exactly how our Sun has functioned for almost 5 billion years. A calm, stable balance between these two forces. But what about Betelgeuse? Betelgeuse was much more massive than our Sun from the very beginning, about 15 to 20 times more massive. And a simple rule applies: the more massive the star, the faster it burns its fuel. You can imagine it like two campfires, one with a small pile of wood, the other with a huge one. The larger fire burns brighter, hotter, and is therefore used up much faster. Our Sun still has roughly 5 billion years of fuel left. Betelgeuse, on the other hand, has already almost completely exhausted its supply in just a few million years. An incredibly short life on a cosmic timescale. And that is precisely why it is so enormous. When a star runs out of fuel in its core, something seemingly strange happens. The core contracts and heats up, but the star's outer layers react in the complete opposite way. They expand. The equilibrium that kept the star stable for millions of years collapses. The outer layers are pushed outwards, further and further, until the star reaches many times its original size. Imagine it like a campfire that flares up wildly one last time before dying out, growing enormously large in the process. Betelgeuse is not a young, active star in its prime. It is an ancient, dying star that has expanded in its final stages of life. And the extent of this expansion is almost unimaginable. If it were placed in the position of our Sun, it would stretch as far as the orbit of Jupiter. Mercury, Venus, Earth, Mars, all would be swallowed up deep within it, lost to a single, dying star. So, Betelgeuse is so large primarily because it is nearing the end of its life and is using up all the remaining material it has. It is essentially consuming itself. One last great flare before its demise. It is, in a sense, a sun in its final stages, bloated, radiant, and on its way to its end. Astronomers predict that Betelgeuse will end in a colossal explosion, a so-called supernova, within the next 100,000 years. This explosion will be so bright that it will be visible from Earth even during the day. Betelgeuse is expected to shine as brightly as the half moon for several months. But this raises an intriguing question. If Betelgeuse is so large because it is dying, how large can stars become when they are in their most active, youngest phase? Is there even a limit? And if so, what sets it? The answer to this question leads us to some of the most extreme objects in the entire universe. And yes, there is a limit. And this limit even has a name. It's called the Eddington limit. To understand what it means, we need to briefly return to the equilibrium I discussed earlier. A star is stable as long as the internal fire pushes outward with the same force as gravity pulls inward. But with particularly massive stars, a problem arises. The heavier a star, the hotter and brighter it burns. And at a certain point, it becomes so incredibly bright that its own light begins to push away the outer layers of gas. But how exactly does that work? How can light push something away? That sounds strange at first. Light doesn't have any force, does it? Actually, light does have a force, and that's not a metaphor. Light consists of tiny packets of energy moving through space at unimaginable speeds. And when these packets collide with a gas particle, they transfer a small push to that particle. Much like a billiard ball hitting another and giving it a little nudge. This is what happens with an extremely massive star. It emits so much unimaginable light, so many tiny energy packets per second, that the combined pressure of all these impacts becomes gigantic. The gas is literally pushed outward, away from the star, out into space. This effect is called radiation pressure, and it's so real that scientists have even designed spacecraft propelled by sunlight, so-called solar sails. With our sun, this radiation pressure is weak enough that gravity easily prevails. But with a star hundreds of times more massive, the amount of emitted light becomes so extreme that the radiation pressure becomes stronger than gravity. From this point on, the star can no longer accumulate new mass. Anything that tries to be drawn in is immediately blown back out. The star is constantly fighting against itself. Its own energy is its greatest limitation. This is the Eddington limit, the point at which a star becomes so bright that it prevents itself from growing any larger. But how large is that limit exactly? Theoretically, this limit lies at about 150 to 300 solar masses. That is, a star 150 to 300 times more massive than our Sun. Such stars do exist. A well-known example is the star R136A1, located in a small galaxy in our cosmic neighborhood. It is estimated to be 200 to 300 times more massive than our Sun and shines millions of times brighter. If you were to place our Sun next to R136A1, it would be nothing more than a tiny spark, beside a gigantic bonfire. However, these stars are incredibly rare and short-lived. While our Sun lives for billions of years, these extreme giants burn through all their fuel in just a few million years. They live very fast, extremely intensely, and die very young. But could a star exist that exceeds these limits? Probably not. Such a star simply couldn't exist stably. It would disintegrate the moment it formed. The radiation would be so extreme that it would immediately blow away the outer layers before the star could even take on a solid form. It would be less of a star and more of a gigantic, self-destructive explosion. However, there is an interesting exception, and it lies far in the past. Shortly after the Big Bang, conditions in the universe were very different from today. Under these extreme conditions, the very first stars could have formed. And according to some theories, these primordial stars were several thousand times more massive than our Sun. We never observed them directly, and they have, unfortunately, long since disappeared. But their existence is an indication that the rules of the universe were not always the same as they are today. In the present-day universe, however, the limit is clear. No star can permanently grow beyond 150 to 300 solar masses. It simply doesn't work. It becomes too bright for its own existence. Its light destroys it before it can grow any further. It's a strange, but also interesting idea that the limit of a star isn't due to external circumstances, but is simply inherent to the star itself. At a certain point, it destroys itself. But what actually happens to these gigantic stars when they truly die? Because their end is just as extreme as their life. When a normal star like our Sun runs out of fuel, it will eventually contract into a so-called white dwarf. Before that, it will expand dramatically into a red giant. And afterward? A compact, slowly cooling remnant, roughly the size of Earth. So, not really as spectacular compared to what comes next. With galactic giants, it's a completely different story. When a star with hundreds of solar masses dies, there is no quiet final phase. Instead, something happens that ranks among the most powerful events in the entire universe. The star's core collapses within seconds, literally seconds, and the outer layers collide with this collapsed core and are ejected outward with unimaginable force. A gigantic explosion, a supernova. This explosion is so incredibly bright that for a brief period it shines brighter than entire galaxies. That is, brighter than billions of stars combined. If such an explosion were to occur in our neighborhood, it would be brighter than the full moon. But with the most massive stars, the true giants, it goes even further. Their explosions are so extreme that they trigger a special type of supernova called a hypernova. The energy released is so immense that it shoots concentrated radiation into space in two narrow beams, so-called gamma-ray bursts. These beams are the most energetic thing the universe has to offer. A single such eruption releases more energy in just a few seconds than our Sun does in its entire 10 billion year lifespan. That alone is almost unimaginable. And what remains afterward is something many of you can probably guess. With the most massive stars, nothing tangible is left behind. No surface, no remnant you could touch. Instead, the core collapses so completely under its own gravity that it creates a point from which not even light can escape. A black hole. That's precisely the ultimate irony of these gigantic stars. They begin their lives with their own light powerful enough to blow away matter, and they end with their own gravity becoming so strong that not even light is powerful enough to escape. From one extreme to the other. These stars are among the most extreme, if not the most extreme things in the universe. They push physics to the limits, forming structures of incredible power where even our understanding ceases to function. This is one of those moments where you realize again how fascinating the universe out there can be.